Now, with complex numbers, we achieved translation by addition. So in order to do the same thing with vectors, we have to introduce a vector addition operation. So here's the basic definition of vector addition. To add two vectors, you just add them entry-wise. Here's the code for doing addition of two vectors in Python when the two vectors are represented as lists. Now, there's always a zero vector, and notice that adding the zero vector to any vector gives you back that vector. Addition has these various algebraic properties, associativity and commutativity, and we'll see how those get used. Now, like complex numbers, we can represent vectors as arrows in the plane. So this vector 315 can be represented with its tail at the origin and its head here. It can equally well be represented with its tail over here. Now, addition can be interpreted as an operation on arrows, just as in the case of complex numbers. To add vectors u and v, you place the tail of v's arrow at the head of u's arrow. And now you draw a new arrow from the tail of u to the head of v. Now, with complex numbers, we're able to scale them, make them bigger or smaller, by multiplying by real numbers. We're going to do the same thing for vectors. So we refer to field elements, such as real numbers, as scalars. And we use them to scale vectors using scalar vector multiplication, which is indicated in this way. Now, I use alpha, beta, gamma, Greek letters to represent scalars in the context of scalar vector multiplication. The formal definition goes like this. To multiply a vector by a scalar, you simply multiply each of the entries by that same scalar. Here's an example. Now let's interpret scaling as an operation on arrows. So here's an arrow representing the vector 315. And when we scale it by 2, we get a vector that's in the same direction but is twice as long. Scalar vector multiplication satisfies an algebraic property that multiplying a vector by beta and then multiplying the result by alpha is the same as multiplying the original vector by alpha times beta. Now, let's start with a vector v, say 32, and consider a whole bunch of scalar multiples using scalars ranging from 0 to 1. Each scale gives you a different size arrow in the same direction. So let's try that in Python. We start with a vector v, represented as a two-element list. Now, we're going to plot a whole bunch of scalar vector multiplications. And you can see it's starting to form a line segment. Let's do the same thing, but with a lot more points. What if we let the scalar alpha range over all real numbers, rather than just the numbers between 0 and 1? Well, the scalars bigger than 1 will give rise to arrows that are longer than the original vector. And the negative scalars will give rise to arrows in the opposite direction. Let's try it out in Python. our conclusion is that if you let alpha range over all real numbers, the set of scalar multiples forms the line going through the origin and the vector v represented as a point. Now, so far we know how to represent lines and line segments that go through the origin and a given vector v. But for purposes of, say, drawing maps, we want to be able to draw line segments that don't necessarily go through the origin. Let's see how we can derive that. We're going to use the idea of translation. So we know how to draw a line segment from 0 to 3, 2. That's just this, the set of multiples alpha times 3, 2, where alpha ranges between 0 and 1. So here's that line segment. What we're going to do is translate that. Now we know that translation is performed by doing vector addition. So we're going to add the vector 0.51 to every vector in that line segment. And what we should get is the line segment from 0 plus 0.51 to 3, 2 plus 0.51. Scalar vector multiplication distributes over vector addition. For example, you can add these two vectors and then multiply them by 2. Or you could multiply each of the vectors by 2 and then add the results. And you'll get the same answer. We'll use that in coming up with another formulation of the line segment between 2 points. So here's our current formulation of that line segment. We take the set of points making the line segment from 0 to 3, 2, and we add 0.51. This is not a particularly nice formulation. It doesn't treat the endpoints in a symmetric way. So we're going to use the distributive law to reformulate it. So alpha times 3, 2 plus 0.51 can be rewritten in this way using the distributive law. Another application of the distributive law gives us this, and we can rewrite that in this way. So now we've got this expressed in terms of the two endpoints and two scalar multipliers, alpha and beta, where beta is 1 minus alpha. So a more symmetric formulation of the line segment between 2 points is alpha times 1 point plus beta times the other, ranging over all alpha and beta that sum to 1 and are non-negative. And this formulation is symmetric. So our new formulation is alpha times one vector plus beta times another for all alpha and beta that are non-negative and sum to 1. Expression of this form, where the scalar multipliers are non-negative and sum to 1, is called a convex combination. And what we've seen is that the u to v line segment is the set of convex combinations of the vectors u and v. We can use convex combinations on vectors that represent things other than points. Here we're going to take two vectors, u and v, that are representing images. One example of a convex combination assigns alpha 1/2 and beta 1/2. This is just the average. And the average of two images is some mix of the two. Now we can also use the idea of a line segment between two faces. So here we're taking a whole bunch of different combinations of alpha and beta to represent a sort of line segment between faces. We can get a kind of crossfade effect in this way. What about the infinite line through two given points? We had a formulation which is not so great. It's not symmetric between the 2 points. But we can get a nicer formulation in this way. Alpha times 1 point plus beta times the other for all alpha and beta that sum to 1. An expression of this form is called an affine combination of the two vectors u and v. And we see that the line through u and v consists of all affine combinations of u and v.